Right. So let's take a look now at part 2 of our bonding series. There's a total of 3 videos on this. Part 2 is going to look at the role of ionic bonding. Now, if we take a look right now at lithium fluoride, the dots, which you now know as the Lewis dot approach, show that there's 1 electron in the valence shell for lithium, and that there are 7 electrons around the valence shell for fluorine. Neither one is stable. Both have to get to a full valence shell. So why don't we now attempt to use covalent bonding strategy? We slide the lithium over. Lithium and fluorine share the 2 electrons, but the system is not stable. Notice that fluorine has 2, 4, 6, 8 electrons. Remember, the bond between them count as 2 electrons for fluorine, and that lithium, using those 2 electrons of the bond, has 2. That's not even close. So this compound is not stable. This compound will not form because you can't satisfy the outside valence shell approach. So one strategy is right. So why don't we create a double bond between lithium? But once again, fluorine has 8 electrons, but lithium has only 4. Once again, not stable. Well, let's keep going. Let's go now to 3. Let's triple bond this bad boy. And when we do that, lithium again has 6 electrons, not the needed 8 to complete the shell. So once again, this whole thing is unstable. We cannot create more bonds. 3 bonds, triple bonds is the limit because the electronegativity, the charge between the 2, is too great. And the result is it's not going to be stabilized. So what you conclude is a covalent bond strategy, sharing electrons, doesn't work here. So instead, what we're going to do is we're going to take the ionic bond approach. And what that means is lithium is going to completely give up the electron that it had in the outside shell. And that's brilliant because now the outside valence shell is empty and the next shell is the inner one and it's full. So lithium actually has a helium configuration, a noble gas configuration, since it dumped the electron. And fluorine, as you can tell, by picking up that electron, now has 8 electrons on the outside. But naturally, lithium now takes on a full plus cation charge, and fluorine takes a full negative anion charge because now they have completely lost or completely gained an electron. Now, as soon as they become ionic species, as soon as these atoms become ionic, there it is now an electrostatic attraction. So what happens is the plus minus of fluorine and lithium combine, and the ionic attraction holds them together. That holding together is the ionic bond. Now, if you were to take a look at lithium fluoride as a solid, it actually is a crystalline structure. It's a white powder that's actually crystalline in nature. Let's take a look at why it forms this crystalline structure. Well, here we have sodium and chlorine. Sodium has 1 electron on the outside, and of course it has the core. And the chlorine has 7 on the outside with the core. And what's going to happen is, let's see if we can get this right. It's not doing it. What's supposed to happen is this electron here of the sodium atom is going to make the jump over to here in the chlorine, and the sodium becomes a plus and the chlorine becomes the minus, and they're going to attract each other. Now, if you do this again and again, what forms is a repeating lattice structure. What you're looking at right there is a crystalline structure. It's also called a lattice structure. And what you do is have repeating plus and minus ions in a very, very regular pattern. And you're looking at multiple ionic bonds called a lattice work. And the arrangements of these cations plus and ions minus, what it attempts to do is the structure will try to maximize as much of the plus minus attraction and try to minimize plus to plus or minus to minus repulsion. And that maximizing and minimizing produces the crystalline structure that you see here. It's very tight, it's very strong, it's very solid, and it's very regular. And this is what it looked like when you pack the whole thing together. That's a crystal. Now let's take a look at another type of arrangement, another ionic bonding situation. You have the nickel heading to fluorine. That makes a charge there. There's electrostatic attraction. And then what happens is the nickel has to dump the next one, so I need another fluorine to dump it too. And they become held together again also. So what happens now is I have this repeating unit whereby I alternate between pluses and minuses to solve it. And this allows for the lattice work to become very, very strong. Now, ionic solids have a very high melting point. The temperature has to be very high in order to melt them. And the reason why is this very regular, very strong, stable lattice structure that creates the crystal means it's very, very hard to destabilize it. The temperature has to get very, very high in order to get the association with the pluses and minuses to begin to break down or melt. So the attraction between the ions, how strong that attraction is between the ions, causes the melting point to get higher and higher if it's stronger and stronger, which is shown by the chart. The LiF attraction is not as great as the magnesium oxide, and so magnesium oxide crystals melt at a much higher temperature than the lithium fluoride. There's another property that ionic crystals have, besides a very high melting point, is they're very, very brittle. Now, why are they so brittle? Well, if we pound the hammer on one particular row, we cause that row to shift. Now, when we shift it one diameter of an atom, suddenly we have pluses lined up with pluses and minuses lined up with minuses, and what you get is a repulsion between the two surfaces. And the result is the two surfaces are going to fly apart. And we would call that property, it's very, very brittle. Now, crystals have a lot of applications in the world we live in. And this chart just shows the different uses for one kind of crystal, which is the sodium chloride crystal or salt. Notice it's used in manufacturing a large number of chemicals that we use on a regular basis, like chlorine gas, Cl2, sodium hydroxide, which is associated with bleach. 50% of all the salt we get is used in that capacity. But as you could tell, there are little other uses, including the melting ice of roads. When you place salt crystals on the road, as they melt, it gives off heat, and that heat causes the ice on the roads to melt, which makes them much safer. It's also a problem for cars because the salt does get underneath chassis that can cause premature rusting, but it's an important safety thing to cause the roads to become safer. How do we get so much salt? There's two different ways to get salt crystals. One is they're found in salt mines, which obviously we can obtain, but also what you can do is you can take ocean water, have it flood a large open flat area, seal off the ocean, and then let the water evaporate over several weeks, and what is remaining is a large body of salt crystals. And in fact, one of these type of facilities are located in San Francisco and is a very common source for us to get the sodium chloride salt crystals. And that is the structure of crystals.